How are you guys doing? All right. So I don't have a lot in the business direction. Everybody having an okay time with the assignments? Make sure to post your videos on the new page that I set up and not on the old page as you write responses to your classmates so that I can see that you did them. Anybody have questions about business stuff? Cool. Then my plan actually for today is to kind of finish up with the sun in some sense, although we're never going to get away from it entirely. Primarily, we need to talk about models for how the sun is powered. And before we do that, I want to review a tiny bit about the gaseous sun model that we've landed on in this day and age. I think I want to do something kind of boring though. There's a number of people on this list that I have here who have not talked to me yet. So I'm just going to like kind of run down this list and call your name. And if you're here and I haven't heard from you yet, and maybe you can remind us something interesting that happened last class that we can catch up on a little bit. Is Beck in this class anymore? Nope. How about, oh sorry, that was Brennick. I'm sorry, Beck is the last name. Nope. How about Kaylee? You're here. Hello. Were you here last time? Do you have any thoughts from last time?
I thought it was really interesting how you said that Jupiter and the Sun orbit each other like a It's not like perfectly orbiting, like just planets around the Sun.
Yeah, Jupiter is kind of nuts. We went through all the planets last time, but Jupiter, you know, most people don't realize this, but Jupiter and the Sun are basically made out of the same stuff in the same proportions. It's a really, really interesting planet in our solar system. It makes up much more, basically more mass than all the rest of the planets combined. It's enormous. But, you know, does anybody have any idea what's the main difference between Jupiter and the Sun? Bridge? Yeah, go ahead. Anybody? Yeah, Michael, right? Well, they both got cores, presumably. I mean, what's the most obvious difference between Jupiter and the Sun?
Jupiter isn't doing hydrogen fusion.
Heck yeah, that's exactly right. Fusion. So there's another class of planets that are even bigger than Jupiter's. And when I say bigger, I don't necessarily mean like heftier, and it's not necessarily wider. There's another class of planets that are made out of the same stuff, let's say 75% hydrogen, 25% helium, and they're called brown dwarfs. Brown dwarfs are really crazy because they're a little bit closer to being a sun. They do actually do a kind of fusion. They fuse what we call deuterium, which is really just a hefty hydrogen. It has an extra neutron. So there's this really interesting crumbling line, and I won't beat on it too much in this course, but we were obsessed with it last semester because the difference between stars and some planets is really, really fine at the end of the day. So that's really interesting. So I'm glad you brought up Jupiter. And yes, Jupiter is big enough that the Sun and Jupiter kind of orbit each other. Of course, the Sun is bigger by a good deal, so it's more like Jupiter orbits the Sun, but still, they orbit a point slightly outside of the Sun. Cool. Let's see, is Nate here in the class? Hey, Nate, what's up, man? Thoughts from last time?
Last class, we talked about magnetism on the Sun. I think it's kind of interesting how it shifts so often, how that affects the cycle on the Sun.
Yeah, it's a huge mystery, too. Magnetism in general, by the way, like throughout the solar system, is one of the most, I'd say one of the more poorly understood pieces of the puzzle. Like, for instance, why do we have this enormous magnetic field? You know, every answer that we can point to, for the most part, you know, that we have these convection cycles of magma under our feet, that kind of stuff. Well, that should apply to several other planets in the solar system as well, and it doesn't seem to pan. At least should apply to Venus, which is kind of our twin sister planet. Tons of apparent volcanism, lots of that convection stuff that should lead to the churning of the magnetic field. it doesn't have a magnetic field at all. So it's really weird. And then as far as the pole reversals, again, it's sort of anyone's guess. And I threw out an idea, one possibility. The other idea would be this kind of tangling loops at the equator. So yeah, magnetism's a real mystery. How about Arthur? Are you in the class still? All right. How about Alex Emily? You're here. Hello.
I don't remember if we actually touched on it in Tuesday or not, but what I found kind of interesting in the reading was that there's a theory out there that the sun might be pulling inward on itself and like consuming itself to be able to produce the energy to keep itself like going.
Yeah, that's so and that's kind of an extension of the old idea for let's say it was called the Helmholtz Kelvin contraction mechanism, right? It's kind of similar to the way a piston in a car works, honestly. Now, of course, a star collapsing on itself is only possible if the star is made out of gas, because you can't really compress a solid or a liquid in the same way. So it's an interesting piece. It's got problems with it as well. Yeah.
Can I actually have a question?
Yes.
Relating to that?
Please.
Stars burn out over like billions of years, right? So,
Most of them.
so sorry.
Yeah.
So
The sun, certainly. Yeah.
It has to power itself. Is it eventually going to burn out? Because we thrive off of, we have warmth. Like that's how humans can survive.
Yeah, it'll be a bad day for sure. We're going to get into all the details of that. So our star is a pretty, I think your textbook calls it a garden variety star. It's a pretty common form of star. I would say most stars are actually even cooler than our star and less dense. A few stars seem to be really, really hot. They're really blue. And so they're presumably going to burn themselves out really, really quickly. And so we'll get into all the details of that. But yeah, nothing lives forever, as they say. And the fate of the stars presumably is no different. And we'll investigate the different ways that stars could end. The famous and popular ways are obviously these explosive, terrifying events. There is interesting evidence to suggest that maybe a lot of stars just sort of peter out too. Which kind of gets into that interesting line that I was just bringing up between the brown dwarfs and the suns, right? So like, what's the difference between a really big brown dwarf and a really small star? Anybody? It's sort of a trick question. Anybody?
Brown dwarfs all the same size or mass, and they just don't have the fusion that a star does.
It's just the mass, yeah. So like if you had a brown dwarf that for whatever reason got a little bit bigger, it would presumably be able to do that fusion. So that'll make more sense after today because we'll talk about fusion. But fusion really comes down to how much stuff you have in one place because you got to cram those atoms together in order to melt them essentially to one another. So that might seem a little trivial, but if you think about it, at the end of the day, there must be stars out there that if you added a single atom onto them, they would have the mass to do fusion all of a sudden. And there must also be stars that if they lost a single atom, they would not do fusion anymore, and they would look a lot like a brown dwarf. So that's a really, and I'm going to expound on that when we get to the lives and deaths of stars, but just to kind of preview that idea, it's a very, it's not an arbitrary line, it's a functional line between the two, but there's definitely reason to believe that stars might have other lives as something more like planets as well, which is really far out. Actually, the Soviets came up with that idea back in the 70s, but nobody knew about it because they weren't talking to everybody else, thanks to the Cold War. All right, how about Ray? Are you here?
I was lucky in the past 2 months.
Oh, that's right, we talked. That's right. No worries, you can email me. Let's see, who else I got? How about Amy? No. How about Trinity? Are you in the class still? Trinity dropped. Thank you for telling me. All right. How about this person I know about? How about Hannah? She's not here. All right. How about Elizabeth? Nope. How about, talk to you already. How about Jeannie or Jeanne? She's sick. All right. Bummer. I think I haven't seen Tommy since the first class. He introduced himself. It must have dropped it. How about Antonio? Are you here? Hey.
Talked about like one thing that I saw in videos that the science powered by helium. So like converts hydrogen to
Yeah, we'll elaborate on all that today. I don't know that we talked about that much last time, but I did see you here, so that counts. Let's see. How about Shay? Is Shay in the class still? No, maybe not. How about Genesis? Are you in the class still? No. Caleb? Nope. How about Carlos? Hello.
I thought it was a little funny how when scientists found out that the magnetic poles switched on the sun, they were afraid that it would happen to Earth too, so they kind of kept it a secret.
They were. So those were astronauts who were in orbit. They were afraid that what they saw with the wingnut, that experiment that I played for you guys, was going to happen to our planet. Yeah. I don't know if anybody else is applying that idea to the sun, honestly. It's just something that occurred to me. I'm sure somebody else has thought of it too. It's just a crazy idea I was throwing out to you guys. But yeah, good point. There's a lot of really interesting, one sec, I'll get to you. There's a lot of really interesting science that the Soviets were doing in isolation. They have, we tend to think of science as like monolithic. Everybody kind of is on the same page about stuff. But the Soviets actually had a really powerful science program, and they weren't talking to people in the West. So they were coming up with wildly different ideas about a lot of things. That being just one example. So, yeah.
A question connected to that I had from last class is that if the polarities of Earth did switch,
Mm-hmm.
what would happen? How would that affect
You know what? Nobody knows. There's a lot of crazy preppers that are worried about it on the internet. And, they might be the ones that inherit the planet. I don't know that it would really matter at all, to be honest with you. I'll tell you the one thing that I can conceive of that would be important. So the reason I don't think it would matter is that almost nothing that we do really depends on, I'm sure it would maybe screw up our GPS for about, a minute until we reprogrammed it. But here's one thing that does happen. When the pole of the Earth reverses, it actually contributes to the disintegration of the magnetic field as a whole. And so nobody knows how long it takes for the pole to invert on Earth. They know it happens regularly, but it's hard to get that sort of time scale resolution. Maybe it takes 5 minutes, maybe it takes 100 years, maybe it takes 1,000 years. It's really hard to tell in the record because the only reason we know it happens is we can see that there's like these, for lack of a better word, there's volcanoes or volcano-like, magma intrusions. And they're spewing out all this magnetizable, so like ironous rock-like stuff, right? Molten rock. And that rock, we talked about how inside of electromagnets, you put like an iron core to stabilize it. It gets imprinted. You guys have probably magnetized paper clips before or something, right? Same thing happens with that rock. And you can see the direction that the magnetic field was pointed, the polarity of it, north versus south at the time of that. And we see regular banding patterns with these. So the only danger that I could foresee is that when the field reversal is going on, the magnetic field essentially disintegrates or becomes so chaotic that it no longer shields us from all the nasty stuff that our magnetic field shields us from. That could be a nightmare for our electronic civilization. So maybe the preppers are right. I don't know. We'll see. We'll find out one day or one century and not too long. It's a good question. What was her name again?
Alex.
That's right. I will learn your guys' names eventually. Forgive me. Okay, cool. Is Diesel here? Not here? Cool. How about Emily Bunton? Nope. How about Asante? How about Stella? Hello. Yeah, it's unbelievable, right? What can I say about that? You know, one thing is really, really bizarre. So the average density of the sun is like about the same as water. It's like 1 gram per cubic centimeter. The Earth is something like 5. So the Earth is the most dense thing in the whole solar system, which, you know, as we talked a lot about last semester, is really perplexing how in the world the densest thing in the solar system didn't end up at the center of the whole mess. So that's a really interesting mystery to ponder. I don't have time to throw my crazy ideas at you guys about that one right now. How about Elliot? Are you here? Nope. All right, I'm almost through this list. Mercedes. Yes, hello.
I like hearing about William Herschel's thoughts on sunspots.
The Solarians?
The sunspot, William Herschel.
Yeah. He had the idea that there was little people living inside the sunspots. Yeah, that's pretty far out. What's even more far out is that he was writing this in the same article where he was discussing, you know, the material structure and the different lines of evidence for whether the sun was a liquid or a shell or all of these things. And he just kind of tossed out this idea that there's people in there and nobody batted an eye about it, right? And it's hard to imagine in today's day and age, like somebody just slipping that into a journal article, right? You're just reading some boring science paper and somebody just throws that out. People were a lot less touchy back then. What do I want to say about that? Which I think was, what I really wanted to impress upon you guys last time by showing you all this is, and I know it got a little boring reading some of the quotes, I apologize for that, but there was really a different spirit of conversation between scientists back in the early days of science. It was really people with crazy different ideas who were exchanging them openly in these letters through the Royal Society. Today, you guys probably don't know this, but you know, being a scientist as a job wasn't a thing until basically after World War II. So all these guys who were doing this work back then, most of them were doctors and lawyers and dentists and, you know, mayors, and I mean, most of them were aristocrats for sure, because for the most part, peasants probably didn't have time to sit around thinking about the material basis of the stars or something. But once we made that transition where people depended, their livelihood depended on their science, it became a lot more conservative, right? People in today's day and age, they really want to work on a problem that's secure in some sense. They want to be able to add details to an existing body of knowledge in a way that people in the 18th and 19th century had no interest in. They were just trying to come up with cool ideas. So it was a very different climate, and there was wild progress in that era as a result of it. So I'm sure I'll touch back on that in the future, but there's a real fear in today's day and age that progress in science is actually kind of ground to a halt. So there's different metrics for looking at that, but in terms of really revolutionary ideas, yeah, we've had a lot of technological breakthroughs. The engineering's going pretty good, but in terms of really, you know, solving some of these huge mysteries, and I've already named a couple of them today, there's not a lot of people working on those because they're not immediately promising if you're trying to build a career, right? If you got mouths to feed, you probably don't want to work on an extremely difficult problem for 50 years before you get a grant for it, right? So it's a weird era, and that problem hasn't been solved, obviously. Okay, and then this person I know dropped the class. So great, I made it through all of you. So now we are around to the third check. Does anybody else just want to chirp in and remind us of anything interesting? Yeah, Terza, right?
Yes, I actually had a question about last class that I wasn't able to get to. So when talking about, again, reversibles about the sun, they observed the sun, they believed that the Earth was similar. And you, I believe, said that they had estimated that it was like every million years.
On Earth, yeah.
On Earth,
Mhm.
but they found no evidence of that. I was just curious how they continue with the theory that the Earth is billions of years old, if even, you know, evidence of these reversals happening within million-year timeframes aren't present.
Oh, they do evidence them. That's what I was talking about with this banding structure. So they have these volcanoes and stuff.
Well, yeah, the structure, but like You said, you had actually said that there was no actual evidence, like physical evidence left to show that, oh, these used to be reversed at one point.
Oh, no. If I said that, I misspoke. So, well, it's not like you can like play a movie back of it, right? So all they have is they have these banded structures. Basically, they have these piles of lava, and they see alternating polarity of the magnetic imprint on these piles of lava. They mostly look under the seafloor. And they say that, you know, this lava took so many millions of years to spew out, and they'll do different kinds of radiocarbon dating and stuff that we talked about last semester. And so they use this kind of indirect signal to say that the polarity of the Earth was different in that time period. Yeah, but I mean, again, whenever we're talking about the deep past, it's all very theoretical still, right? There's definitely pieces of the puzzle that you can point to, but at the end of the day, you got to stitch them together into a story. So, you know, I like to tell people that they should try to put together as many stories as they can find, really, and really sort them out on their merits at that point. It's very dangerous to get into a point where there's only one story that you're willing to look at. Which is kind of an interesting thing, which is why I think it's so important that we at least allow people to present their stories, no matter how crazy they are. You know, anybody listen to the Zuckerberg interview on Joe Rogan that just came out? Nobody? I mean, it was kind of horrible, but one thing that like particularly disturbed me about it was that, you know, Zuckerberg just came out and had this big statement, like, we're really sorry at Facebook for censoring people's ideas, yada, yada. And at some point in the interview, he's like, well, you need some censorship because, you know, terrorism and stuff. And it's like, okay, fair enough. Like, people are advocating murder and violence and stuff. Like, okay, we can't let people post that. But then at some point later in the interview, he started to conflate like flat earthers with people that needed to be censored, which I thought was like a really dangerous idea, because I'm like, look, I don't think the world is flat, but I'm certainly not afraid, or I don't think it's dangerous that somebody thinks that at the same time, right? And if you start throwing out ideas that you think are stupid, well, then you're gonna potentially miss some really interesting gems because they're not popular ideas. And so this is something that actually I lose a great deal of sleep over, which is, you know, the information space that we have today. There's not this open dialogue, and that's what I'm trying to kind of get back to you guys with today. It's like, you can have really, really functional models of things that are completely wrong. And last semester, the central story that we circle around is the heliocentric versus geocentric model with Galileo and Copernicus and the church and all of this stuff, right? And the textbook loves to point at this story as like this wonderful example where we thought that the Earth was at the center of the solar system, but we were wrong about it. And isn't that great that science triumphed over this and everything? The problem is with that story that, and I don't know if you guys realize this, the Earth at the center of the solar system mathematically works out perfectly. It's an absolutely useful model. It tells you exactly where the stars are going to be, or where the planets are going to be. It's a really accurate model of the solar system, right? So you can't just evaluate something on whether it works or not. Things can work and be completely wrong, and that's a great example of it. So, yeah. Anyways, I just worry a lot. This probably doesn't concern you guys too much, but it might as you go forward in the world. So that's my plug for open access to information. What else? Any other thoughts from last time? So, yeah.
I kind of found it interesting that back when we were using the telegraph, like how like the solar flare was like so bad that it knocked it out.
That's a real problem too. That definitely is on our horizon, it seems like. It's a pretty common feature.
I remember like there was this one time, I think it was the year where like the Borealis was like more present, where like there was solar flare and like it knocked out like our projector in the classroom.
Really? Wow. That's pretty crazy. Yeah, so that probably wasn't even a very big one compared to like the Carrington event. Yeah, that'll be interesting. I think that we'll see that play out in our lifetime. Hopefully it's not a big disaster. Hopefully there's not a lot of panic too, which can sometimes be the bigger disaster. Yeah. Any other thoughts? All right. All right, so look, as we move towards trying to understand how the stars power themselves, you know, I in this course in particular, I spend a lot of time kind of picking on like popular ideas because there's obvious holes in them, but I don't want you guys to think that I don't think they're valuable at the same time. So, you know, this is a map of the world from, let's say, right after early European contact with the Americas. This is obviously not how we think the world looks today, right? But it was a really useful model to the people who were driving around in sailboats, little tiny wooden boats on the huge ocean, right? They were, in some sense, able to actually navigate the Earth and find their way to where they were going, more or less, right? And I think that that's a good way to think about what we're trying to do in astronomy and astrophysics in general, is come up with progressively better maps of what the heck is going on. So the map that your textbook presents about how stars power themselves has some serious problems, and we're going to talk about them today. But there's probably some really useful stuff in there too. So, you know, I really just want you guys to think about this project of science as this unending endeavor where we're always updating our understanding, right? You know, we have incredibly accurate maps now, but it's only possible essentially because we can fly satellites around the Earth and map the thing directly with photosensors and every other kind of radio waves and radar and all sorts of wonderful technologies, right? So we have incredible maps of the surface of the Earth at this point. And that's just the nature of the beast. That's how it goes. So it's okay that we're completely wrong, you know, but we also have to have the humility to admit when there's problems. We can't just act like there's no problems, because otherwise then we get stuck with something that won't serve us very well. And I do think that burning oil in cars is becoming a rapidly medieval way of powering our civilization. So I don't know if you guys realize it, but pretty much everything in this classroom is made out of oil, right? So your chairs are made out of petroleum byproducts. The carpet's made out of petroleum byproducts. Your clothes are mostly made out of petroleum byproducts. It's just a really dirty, kind of gross and inefficient way of powering a civilization. So we look up at the sun and we're like, wow, if only we could do that here on Earth. That would be fantastic. And I think a lot of that depends on these very principles that we've been laboring over, such as how the sun is structured, how does it work, how does it do this magic, how does magnetism work, what are the actual atoms doing to each other? These kind of nitty-gritty problems that seem a bit esoteric and abstract and beyond practicality, I think they have real-world implications. So, you know, we have to take all of this with that grain of salt that, yeah, we should be forgiving of ourselves for not having all the answers, but we can't give ourselves a pass on things that don't make sense at the same time. Which is a huge reason why I've spent, you know, at least a good portion of the classes so far banging on about this gaseous sun. And so I want to just one last time review with you guys the reasons why astronomers and astrophysicists, for the most part, believe that the sun is a gas at the moment. Does anybody remember a single one? I know this was deep into the history books. Why do people think that the sun's made out of a gas? Anybody? Yes, please. Don't be timid. It's all right.
Isn't there that theory that no matter how much pressure, it will always stay a gas?
That's right. Yes, yes. So Andrews critical temperatures. So Andrews was a very famous scientist back in the 19th century, and he did a number of experiments where he showed that you could compress hydrogen as much as you want and it would still remain a gas. Unfortunately, Andrews didn't have access to the kinds of pressures that we would need to achieve in something like a Jupiter and in something like the Sun, which has enormous pressures, really not that deep into the thing, right? The alternative hypothesis to the Sun being a gas would be that it's some sort of liquid metallic hydrogen of a sort, and that liquid metallic hydrogen is metastable, which means that even when it depressurizes, it remains in that phase as it bubbles up in those convection cells and so forth. So they didn't have access to that information, and that's going to be the case with all 5 of these points for the most part. At least 3 of them have been patently scientifically disproven at this point, including this Andrews critical temperature. 2 of them are a little more tricky. Does anybody remember any other reason why people became convinced that the Sun was a gas? Yeah.
The line in the emission spectrum is outside the sun, which is a gas.
Yeah, there's definitely gas in the atmosphere of it. There are lines. And related to that was the realization that if you squeeze gases, the lines become broader, so they can exhibit tangential frequencies, right? So not just a single line, but they actually broaden a little bit. And so the hope was that you could reassemble something that looked like that beautiful rainbow spectrum from a bunch of broadened lines, essentially. And you know, that's a really interesting, hopeful situation, but nobody's actually managed to produce a black body spectrum by squishing gas ever. You won't be able to find any experiment that's done that. So it's a bit wishful thinking. Anybody else? Yes?
I think it's kind of similar to theirs. It's that sort of like compression, there's temperature that makes it so it can't be liquid, or in the past couldn't have been like liquid or solid because they couldn't sustain their form in further state with how hot it was.
Yeah, that's all related to the phase diagrams, right? So temperature, pressure diagrams, yeah. And that came down to the fact that a lot of this work was done before we had access to those actual temperatures and pressures that we do today. Anybody else? I mean, the real clincher, so bouncing off both those ideas, the gentleman who did all of the initial black body work, he really, and this is a problem with physics in general, most physicists, they want their theory to apply to the whole universe, right? It's called universality, and it's generally considered a feature that makes your theory more powerful. The guy, Kirchhoff, who did all of the black body work originally, he really, really wanted his laws of thermal emission to be generalizable to all of matter everywhere in the universe. And so he sort of succumbed to that temptation, particularly when he saw the pressure broadening and Andrews' revelations about the nature of temperature and pressure on hydrogen gases. There's kind of 2 more big pieces to this puzzle. Does anybody remember either one of them? Yeah, in the back.
The nuclear fusion that's going on, like turning the helium into the hydrogen.
That's a huge one. Yeah. Let me save that one for last because that's where I'm going to go with everything next. So let's hold on to the fusion for a second. What's the other one? Anybody from last semester? It's the formation model for the entire shebang, the whole solar system, right? This idea that a swirling ball of gas collapsed and made the solar system was a really old idea. It was hatched, well, some version of it's probably persisted for thousands of years in a mythological form, but the scientific advancement of it, or the philosophical advancement, was brought forth by a few different philosophers, notably Kant and Laplace kind of tooled up the math to make it work. But people had this idea that that's how you get a star in the first place, long before they had any idea what a star was. So this idea of things collapsing upon themselves and squishing down is really a situation that's much more amenable to a gaseous state than to anything else. It's very hard to compress liquids and solids, right? And so the final one, remind me your name? Kevin. The one that Kevin brings up is how the heck do you power a star, right? So originally, people had taken that idea that the whole thing formed through this collapse mechanism, and they were starting to play with engines, heat engines at the time, and they thought, oh gosh, like you can do this in an engine too. You squish it and you get heat out of it, basically, right? This is kind of internal combustion engine 101. Well, that held everybody for a while, except eventually someone pointed out that they did the back-of-the-envelope calculations. Actually, they probably did very deep calculations. And they figured out that if you compressed all of the material in the sun in order to ignite it, it would only last for, well, geologically speaking, only for a hot minute, something like 100 million years, right? But there was all of this geological data, this not archaeological, what do they call it? Paleontological data, right? So about dinosaurs, stuff like that, where people were starting to think that the Earth was probably billions, so thousands of millions of years old. And that model that the sun would just use itself up in 100 million years became untenable. So enter this gentleman named Arthur Eddington. Arthur Eddington, gosh, it's hard to find a parallel for Arthur Eddington. He's kind of like if you had a hybrid of Neil deGrasse Tyson and Barack Obama and jeez, I don't know who's
Say Dolly Parton.
Dolly Parton. He was super charismatic, super smart, super likable, and he just had a way of making friends. And I think I pointed out to you guys right at the very end of last class that he was the guy who basically brought Einstein to the West, right? So he read Einstein's papers on relativity, photoelectric effect. No doubt Einstein had some brilliant ideas. He actually got his Nobel Prize for some work that had nothing to do with all of those famous cosmological things, which was actually about how light produces electricity, so sort of like solar panels, that kind of stuff. But Arthur Eddington found that guy. He discovered him, let's say, and brought him to mainstream attention. But Arthur Eddington also had this idea that the newly conjectured idea of fusion, so that atoms could be squished together and they would release some energy, that could be a potential way forward. Now, he had that idea almost 30 years before any actual fusion experiments were available. It was just a complete theoretical idea. But Eddington was able to eventually use this contractile method of the solar nebula collapse, right? He was able to use the ideal gas laws and to propose an idea by which fusion could be achieved through the compression of these ideal gases. So he made a mathematical representation of this. We call these the stellar, these are the equations of state for the sun at this point. And some modified version of Eddington's equations of state are still the ones that are used to this day. They're also very relevant to the fusion researchers that are trying to squish balls of gas together in the laboratory to make fusion reactors, which are always 10 years away from happening at any given point in time. So Eddington appears on the scene and gives us this fusion model that we're going to be talking about today. So, the fusion model that we're going to be talking about today takes place entirely in the core of the star. So the core of the star is the only place where you have high enough temperatures and high enough pressures to basically force a gas together into the kind of collisions that are inelastic enough, right? They can't just knock around, that you could actually squish two atoms together. So with a gaseous sun, fusion can only happen inside of the core of it. Now, this was nice too because what it allowed them to do is propose this other model by which theoretically they can generate that continuous spectrum of the sun. So the idea that emerges from that is that all of this all these fusion reactions that we're going to be talking about today, they give off some light. It's a really high energy light, actually, gamma rays, right? Really high energy light. But what happens is the light bounces around inside of the sun for millions of years, and then by the time that it gets to the surface of the sun, it emerges in all the right frequencies to have it fit perfectly into this black body spectrum. I have no idea how that passed peer review at the time, but that is the standard mechanism by which we get that black body spectrum today. So Eddington kind of tied all of this up. He also got wildly famous off of Einstein, right? It's kind of like discovering Shaquille O'Neal or something like that. And so people loved it and ate it up, and they've been working off that model ever since. So at the core of this whole discussion is these magical symbols and this concept of energy, right? I thought it'd be interesting to actually read you what your textbook says about energy, because I find it really cringe, and I was hoping to do a better job of it. So the textbook says, energy is a challenging concept to grasp because it exists in so many different forms that it defies any simple explanation. In many ways, comprehending energy is like comprehending wealth. There are very different forms of wealth. They follow different rules depending on if they're the stock market, real estate, collection of old comic books, great piles of cash, or one of the many other ways to make and lose money. It's easier to discuss one or two forms of wealth or energy than to discuss the concept in general. And I'm like, oh boy, is it really that complicated? And I think energy actually, the reason that I want to spend some time on this is because I think energy is actually the most abused word in not only all of science, but perhaps ever. So, you know, what the heck does energy mean? People use it like, how's your energy today, right? Or we want clean energy, right? Does anybody want to take a crack at a very simple conception of what energy actually is? Yes.
It's like the force that makes things go forward. I'm trying to describe it like kinetic energy.
Yeah. Kinetic energy is a good restatement of it. A force that makes things go forward. All right, sounds very supernatural. May the force be with you.
It's a wheel turn,
you know, just some magic sauce that's inside of everything. Yeah, Levin. It is a communication between atoms. I would say light is a kind of communication between atoms, and light is an energetic process. But I'm looking for something more general, like really, really general. Okay. I hear the word motion, right? What is motion? Yeah. I mean, what is motion? Like, what does it mean if I move? What's happening exactly? Yeah, that's right, Kevin. I'm relocating, right? So motion is simply the relocation of a body. I like the word body, actually, in physics a lot. It's the one that people back in the 18th, 19th century used. Today, you hear the word object a lot. I don't like the word object because the word object for mathematicians can mean a set of variables. It can mean a matrix of infinite dimensions. It's a very confusing thing. I would say that in language, so I'm speaking some kind of language right now, every single word that comes out of my mouth is either representative of a body or every single word in the English language and every language is representative of a body or of a concept, an idea. And what's the most simple concept imaginable? Motion. Because all ideas eventually refer back to a body, is the truth of the matter. Because that's the world in which we live in. I got tables and chairs and, you know, sun and rain and all of these interactions, but they all depend on the activity of bodies, right? And so you can infinitely abstract yourself away. Humans are incredible at this. This is, I would say, what our superpower is, if we have one, is that we can always come up with relationships with other relationships. So I make the most simple idea imaginable would be the relocation of a body. You just move something, right? I just have to refer to where it came from, where it is now. Now I can compound that and make it a more complicated abstract relationship by talking about how fast it happens, so comparing it to some standardized clock source. I can talk about what color it was, right? I can do all of this stuff. I can talk about, I can I can compare that motion to another motion. I can infinitely abstract motions and motions and motions. And eventually I can come up with, human activities, right? Everything from baseball to going on a date, right? These are all essentially can be boiled down to motions too. So motion is at the heart of this concept, right? And if we look at the Greek word, I'm gonna not even try to pronounce this in Greek, but it's something like energia, like that. It means activity, right? And so what's really fascinating is that people worked on this idea of energy. They had this sense that that motion in itself was conserved, right? That each body was imbued with some state of motion, whether it was visible or not. It might just be hot. And we eventually learned that heat represented actually molecular motion. But that motion was conserved, right? So if I cool off, let's say if I warm up an ice cube, then I cool down something else, right? You can't just, the universe is imbued with a state of motion which appears to be unchanging and eternal, at least a closed system, right? And, I'm sorry I brought the universe into this, but if we were to just look at any closed system, that energy, that activity, the motion with respect to how much stuff is moving is conserved. So the way that we've always classically defined it, the original form of it was called vis viva. This is the form that you're probably more comfortable with, which is kinetic energy. Somebody brought that up. Who brought that up? Somebody brought that up. Yeah, kinetic energy, right? Basically the same concept. There's a half involved in kinetic energy because you actually have to accelerate something to its final velocity, and so you actually take some energy to do that. That doesn't matter. The point is, if you look at these equations, and you don't have to really be able to read math to understand this, you have something, which is described by the m, right, the mass, and you have some motion, which is described by the velocity. So you have something doing something, always. So energy always refers to something doing something. That's it. So I tend to define energy as material in motion of some sort. I think that's a really good basis. And I don't think that it's beyond the grasp of, intro astronomy students or anything like that. Now, we can break that down into all sorts of different possibilities and different ways in which it's exchanged. And of course, the equations can get really scary and disgusting quickly. But the bottom line of the idea is pretty foundational and simple to understand. So, questions, thoughts about energy? I think to some extent, even that definition works in the more poetic, abstract sense when people are like, how's your energy today? It's like, well, how are things like kind of flowing for you, right? It's like, this is generally what we mean with that word. And I think that's worth keeping in mind as we go forward. So your textbook, for some reason, wanted to point at the famous E equals mc squared equation. Again, this is a restatement of something moving, presumably at the speed of light. Now, this equation actually refers to the rest energy of something. So we would say that even an atom, or let's say an atom, would have a rest energy to it. And you might think like, wait a second, how the heck does an atom have a rest energy? Like, how can something at rest have energy to it? Any ideas? Yes. It's always moving. There's something within it. It has internal subunits of some sort that are in states of freneticism, right? And it turns out, that those various states of freneticism give it different shapes, right? So, as you glom on more material to the atom, it can vibrate in new and interesting ways. Also, as you just excite it with more and more of this motion, you can get really beautiful shapes for the different lobes of the outer electron of the atom that start to appear. And this is really interesting, kind of beyond the scope of our conversation, but what's really cool is that as the atom gets into these new frenetic states of motion, the electron surface of the atom, these surfaces take on new abilities. We would say that they have different charge abilities, they have different magnetic properties. Essentially, those motions are conveyed, right? And I've kind of touched on this before. how some of this might work with respect to the transfer of charge and things like this. At any rate, it's not magic, right? So it is an atom. It is some sort of material in motion doing things to its neighbors. And that's how we get all of these processes that we're about to dive into. I wanted to say something else about this. So speed of light. I think it's as good of a time as any to talk about the speed of light. Really fast, right? So light is the conveyance of the motion at the surface of one atom to the next, right? So this kind of motion we call charge. And when you have light, what you're doing is you're actually alternating the charge at the surface of the material, right? So if you look at, if you want to build a really simple electric light, you might call it like an antenna for sending radio waves, right? The way that antennas work is you alternate the plus and the minus on a wire back and forth, and you basically generate a radio wave that has that same character to it, that same quality. It depends on the rate at which you alternate that charge. All of light works just like this. So you're communicating this change at the surface of one atom to the next. Now, we talked a little bit about the disappearance of mediators in physics, right, for fundamental phenomena like light, gravity, electromagnetism. People don't really worry about it anymore, right? How does the light get from one atom to the next? Doesn't really matter. We couldn't find the ether, so meh, forget about it. There is something interesting buried in there, though. So if there was to be a mediator for light, we can learn something about it by the speed of light, I think. And so, you know, the speed of any wave in any material depends on two things. It depends on how dense the material is, and it depends on how stiff it is. So generally speaking, the less dense something is, the faster the wave travels, and the stiffer it is, the faster the wave travels. And we can measure this in any material, right? If I just hit if I hit my hand on the table and I measure how long that wave takes to travel down the table to some measuring device over here, and I vary the stiffness of this table, I can actually speed up that wave. So since the speed of light seems to be the fastest thing that we've ever seen in the universe, we can assume that if indeed we were to ever pick up this search for the mediator, which I've suggested to you might just simply be the atoms themselves in some extended structure, we know for a fact that that medium must be extremely stiff and it must be extremely rarefied, so very low density, right? And that's really, really fascinating too. So C, really, really fast, a lot of energy inside of even the tiniest little things because they're presumably moving at that extremely fast speed as they do their dance. All right, so your textbook then moves forward and talks about some of these fundamental particles that are going to be part of the balance of the reaction that we're going to be talking about with respect to fusion. So I think this is maybe the second most misunderstood word in all of, well, just restrict it to physics, but perhaps chemistry as well, is the word particle. Does anybody know what a particle is in the sense of fundamental physics? All right, what's a particle in your everyday life? Yeah. It's a little piece of something, right? Can you say that? Like if you have a particle of salt, or like I don't know, what kind of particles do you guys interact with? Dust? What was it? Hair particles, sure. Or anybody do 3D graphic design? Anybody in digital media here? No? Particle systems, right? They're just like little flecks, little dots of something, right? Points, almost. Okay, so the word particle in general parlance, before the mathematical physicists got a hold of it, really just meant a little chunk of something. Unfortunately, that's not really what we mean when we talk about particles like these: the proton, the neutron, the electron, and the neutrino. What's the main difference between a mote of dust and a particle like an electron, for instance? Yeah? Okay, I like that. That's very close. So he's saying it has a particle of dust has a specific location. It has a position. Yeah.
Particle of dust could be broken down to see the composition, whereas it's hard to know an electron.
That's a really good point too. Yeah. So these are considered in some ways indivisible, right? Although that's not totally true for like the proton. There's supposed to be substructure to it. Anybody else? I would say that the fundamental difference between the mote of dust or the particle of salt or the particle of hair is that those things are bodies, right? They're defined by their structure, which is essentially a surface that separates the outside from the inside. So you can visualize them, you can imagine that they essentially have architecture to them, right? A particle of dust. You'd have to get a really nice microscope to see it. But the particles of the physical world that we were used to prior to mathematical physics were bodies. These are not bodies, and I'll tell you why. Bodies don't have motion intrinsic to them in order to be conceived of and defined. So if I want to describe to you this bottle here, right? I can come up with a series of equations easily to describe, well, not easily, somebody could, I don't know if I could do it. Somebody could make a series of equations using CAD or something like that to depict this bottle. You know, another way of thinking about it is you could draw a picture of it, right? It's defined by its architecture alone. There's no moving pieces about this bottle. There's nothing, the bottle isn't in motion, right? If I was going to explain to you what a bottle is, I don't have to tell you how it's moving. That's the fundamental difference with these particles, is that they all have some intrinsic motion to them. So the electron, for instance, has actually all of these have an intrinsic momentum character to them. They have an intrinsic angular momentum that we call spin. And it's like, what the heck is that? Well, it points to some aspect of it that's changing in some angular fashion. There's some rotatory aspect to it. I guess what I'm trying to boil this all down to for you guys, is these are events, actually. These are not bodies. These are bodies in motion of some sort. Now, they might be complex bodies with substructure, as we already have intimated with the proton, for instance. Maybe the electron is a body, maybe it's just the outer surface of the atom in some state of predictable motion that we call the electron, right? So this word particle is like terribly abused because it's not actually referring to something that you can actually statically conceive of. It is something happening, right? And it's happening in a very regular, pattern, predictable fashion. So these are really useful concepts. Obviously, we've used the electron to no end in order to account for processes that have allowed us to develop all this wonderful electronic technology that we're using right now in your computers, your phones, everything else. But in terms of what it's actually meaning, it's meaning something that those atoms are doing. And we're just not there yet with what that actually is. Okay. You know, mass is another one of those words that's a little bit abused as well, which is worth mentioning too. The word mass actually was developed to refer to gravity, right? So you would have a mass that's accelerated by gravity, you would determine the mass. So all of the atoms have masses to them, right? But the atoms themselves cannot be thought of as a mass, despite the fact that's something that people say often. Now, the reason for that is because the mass is actually a quality. It's an idea. It's not actually a physical body that you can move around. And this gets abused. There's actually a philosophical word for this fallacy. You guys know what a fallacy is? It's like an error of logic, right? So if you take any philosophy courses while you're here, you'll come across this. There's a great enumerated list of fallacies that people make, and often they make them in rhetoric. So if you watch like presidential debates or anything like this, sometimes you'll hear people say like, you know, this person made this kind of error of logic, and they'll call it a fallacy. There's tons of these. The one that's at play here is a fallacy called reification. Reification is when you take something abstract and you treat it like it is a physical object. So it wouldn't make a lot of sense to you if I was like, hey, can you toss me some sadness? It's like, what? What are you talking about, right? But we do it all the time with these concepts, right? These are not bodies. These are concepts, but we move them around. We apply motion to concepts, and it becomes very, very confusing very, very quickly. So anyways, I just wanted to tip you guys off to that. I think it actually is really, really important as we get forward into these nuclear reactions, because we don't really understand what the heck is going on at the center of the sun. We understand a series of equations that give us a balance for how these processes play out. So this is called the proton-proton chain reaction. This is the theoretical heart of the sun, where all of the juice is generated, so to speak. And as somebody previewed earlier in the back of the class, it's a pretty interesting and circular process that makes a lot of sense on one hand, right? So you squish two hydrogens together, you get a heavy hydrogen, it gives off a backwards spinning electron that we call a positron, and this little extra bit of energy, which we call a neutrino, whatever the heck that is, some sort of activity that's frenetic and can be transferred. It's a bit, I think of neutrinos a little bit like in the same domain as light or something like that. It's some sort of transmission of energy between atoms at a distance. Then we can take that heavy hydrogen, so it's got a little bit of extra goop, it's got some more mass. We would say that it has an extra neutron, although that's debatably an accounting trick too. We take that heavy hydrogen, smash it together with a regular hydrogen, and all of a sudden we get a new element, which is this helium. Helium, this reaction gives off a little bit of light, really high energy light. We call it gamma ray. And then these guys can interact to make an even heavier helium. And the whole process gives us back a hydrogen, and the whole thing can recycle and repeat. Now, there's much, much more complicated steps. So you probably notice, I don't have any easy way of pulling up this periodic table, but hydrogen and helium are the two littlest atoms that we know of. They're about as simple as it gets, right? And you might ask yourself, where does the rest of this stuff come from, right? Because like iron is something like 50 times more complicated and massive than a hydrogen, right? We have lots of iron all around us, right? It's in the metals, it's in our devices and so forth. There's all sorts of metals. There's huge, heavy atoms everywhere. So where in the world do those come from? Anybody? Not in our sun. Yeah. Nope. Fission is the breaking apart of atoms. Yeah. Yeah, supernovas. That's so other stars, huge stars that can squish more stuff together than simple hydrogens is the answer, essentially. That's the best answer that anybody's come up with. There's some other ideas too. There's obviously something absolutely insane going on at the center of our galaxy, and many people have pointed to that as a possible source of heavy elements as well. But our sun just does the basic boring hydrogen and heliums. That's what it makes. And it starts with hydrogen, so I don't know if you can give it credit for that one on creative grounds. Now, this is a pretty lovely story. I like it. In some respects, I think there's probably, I think our sun probably does do a lot of this in one way or another. There are some interesting counterexamples, though, which I think are worth mentioning. So, I'll get to that in a second. So this requires, this process, we can do this process on Earth. It requires enormous, enormous temperatures, millions of degrees Kelvin. I guess they're just called Kelvin, millions of Kelvin. And this is essentially the process that we are trying to base our fusion reactors on today. So the way that we do fusion in most of these laboratories is we take some gas and we squeeze it from all sides. We get it really hot so that it's ionized, it's conductive, and we squeeze it with magnets really, really hard, and then we zap it with a laser, and we hope to God that it'll stay put long enough to give us a little bit of energy back. And it's very, very, very difficult to get those gases to sit still in one place long enough to get anything meaningful out of them. So this is the process that we're pursuing in our modern age. Now there's another option. I'm gonna touch on that in a second. But before we do that, I think there's reason to believe that there might be some other processes happening. Now, why do I say that? So there's this really interesting star. There's probably more stars like this, but this is one that people have written about a lot. It's called Cebulski's star. Now, the interesting thing about Cebulski's star is that Cebulski's star has elements in its atmosphere. So we can tell, remember, we talked very briefly about the solar atmosphere, the corona, how you can see these lines in it where you can tell, that's the fingerprint of this atom or that atom. Cebulski's star has elements in its atmosphere. Let me make sure I get this right. Like Einsteinium. Einsteinium has only a half-life of 472 days. That means that as soon as you make Einsteinium, it's a huge heavy atom, it's a huge metal, really, really heavy. As soon as you make it, you can make it in a laboratory by squishing stuff really hard. As soon as you create it, it decays into something smaller through fission. Somebody mentioned fission. It decays through nuclear decay in a matter of days. So how in the world does Cebulski's star, which is not a particularly enormous star, by the way, how in the world does it have elements in its atmosphere that could not have survived more than a year or so? Not supposed to be creating them, right? So Cebulski's star should only be really creating hydrogen, helium, same as our sun, right? So there's something weird going on. It's really funny if you, I've never talked to any of the researchers who worked on Cebulski's star, but if you read the Wikipedia page, the go-to explanation is aliens. They're like, aliens are dumping their trash into the star. Maybe. I'm like, maybe. Or maybe fusion isn't just happening inside of the core of these stars, right? So there's this other possibility. I brought it up before. And this is, I'm not sure if I put this in your Moodle, but I shall, which is the idea that you can actually fuse things inside of lattices, inside of actual material structures as well. I actually, I tried again to get in contact with the authors of this work, and they finally wrote me back today, which I'm very excited about. So hopefully I will have them on my podcast soon, and we will get to the bottom of this. But it's a really interesting, promising approach, which seems to be completely ignored in terms of the possibilities for astrophysics. And if it is possible that the stars, actually in their surface at least, or at some depth, are able to form lattices, let's say it's not actually just a kind of formless gas, but it actually has a liquid layered structure to it, then you can imagine squishing elements in between little pockets of that, right? Upon which the entire pressure of the system can work together to squish it together and actually get fusion reactions at upper depths. So in my mind, at least, there's a good reason to believe that fusion, not only on Earth, has a more promising avenue, but actually in the stars as well may be happening, and not just in the cores of the stars. So, yeah, that's an interesting possibility. And I was delighted to see that there's a very famous physical chemist who recently published this letter named Annemarie Bogaerts, who actually acknowledged in the paper the possibility of the ascendance of a more liquid model for star composition instead, which would be capable of all of these high energy nuclear reactions. So, all right.
So is that pretty exciting to you because you worked in like water research?
It makes sense to me, yeah. I think that it's exciting to me because, for a couple of reasons. It's exciting to me because once I once somebody pointed out to me that you can't possibly get that continuous rainbow from a gas, I was very disturbed for a little while, because I find like, I think just like you guys, like I want to know how things work. And if our best and brightest minds are telling us that the sun works in one way and it doesn't make any sense, I find that really disturbing. So having another avenue towards something that is more promising, for me is like more of just like a spiritual satisfaction, like, okay, at least this makes sense. It's also technologically exciting though, I think, because like I kind of opened up class today, the way that we generate power, our material civilization is like a little bit yucky. I don't know a better word for it. We make a lot of waste. Even our nuclear energy is promising, but it also has, this is fission, not fusion, makes a lot of really scary waste that we basically bury in mountains. We don't know what to do with it. It's probably better than coughing a bunch of smog into the atmosphere, but it's still dangerous. So the possibilities that we have for moving ourselves around the world, we can develop better carbon scrubbers, we can make more efficient engines, we can get electric cars, but how are electric cars powered? Exactly, well, not diesel, but it's using coal for the most part. Yeah, so, I mean, that's a non-starter for me too. So I'm like, look, the sun obviously has it worked out. It's been burning for a really long time. And if we could figure out how to do that, that would be freaking awesome. I think that would be one of the, I think it will completely remodel civilization once we figure that out. I think that, I don't know about you guys, but a huge part of my bills is energy, right? Gas. I mean, I live in Grants Pass. I got to drive here. It's basically all my gas money. It's basically my entire money from getting paid to teach this class to drive out here. Not really, but almost. And gas, like heating your house, right? Flying places, right? What if all of that was super cheap and easy and abundant and available? I mean, that's a cynical perspective. I don't know if you're wrong about that, but I hope not, I like to think that the good guys win out over time. But the point is that something really beautiful would be possible if we were able to figure out how those stars worked. And so I am very excited about seeing articles like this come out that kind of recognize that there's an elephant in the room, which is that treating the star like a ball of gas doesn't make any sense at all. And if we keep pursuing that avenue, I think we'll be stuck right where we're at for a very long time. I also think that, moving forward, we're going to start talking about other star systems. We're going to start talking about the organization of the galaxy, the fate of the cosmos, all these huge, heady questions. And, the answers that we arrive at turn out to be really, really different for a liquid model of stars versus a gaseous model of stars. And I think you guys might not like those answers as much because they're not quite as fantastical and as exciting as world-swallowing black holes and stuff like that. But I do think that it's productive. And so, in so much as the understanding of nature matters to you, and in so much as technological progress matters to you, I think really re-examining the material basis of the stars is going to be absolutely critical to the future. I think it's just going to be one of those things, like, I don't know how long this is going to take. Could happen next year, could happen 1,000 years from now. People had the geocentric model of the solar system for 2,000 years. They were totally fine with it. It kind of worked, right? It was very predictive still. It was just wrong, but it worked. So, could we keep limping along with these kind of half-baked fusion reactions that, the headlines tell us we're going to have fusion 10 years from now for the next 300 years? They keep saying that. Could happen that way. It doesn't have to, though, which is why I'm really excited to share this stuff with you guys here. Not that any of you guys are going to become solar physicists, but just getting this idea out into people's mind, I think, is really, really important. And it's something you guys, I think that actually the fracture at the heart of astrophysics, which I've kind of introduced to you guys at this point, is something you can explain to a child. It's actually really, really easy to do. If you grab a prism, you can actually I don't, you know, Levin actually pointed out these are LED lights, so that wouldn't work as well. But if you have like a fluorescent light and you have a sun, which we all have a sun, you can see this, you can show this to a child that you get a very different spectrum from a gas than you get from a star or from a anything heated, like you can just look at the coals in a fire, for instance, right? You're going to see that same rainbow. Anything that's heated, any glowing body that's liquid or solid is going to give you that nice black body curve to it. So it's kind of an obvious situation, honestly, and it doesn't require an advanced PhD in astrophysics to make sense of. So I don't know when that paradigm's going to snap, but it will snap. I'm 100% convinced. So there we are, folks. We're going to leave the sun behind now, unfortunately. It is the Rosetta Stone to understanding everything that comes downstream of it. But yeah, I don't know. Think about it over the weekend, and we will pick up with the rest of the universe on Tuesday. I hope you guys have a good weekend. We'll see you then. Yep, for sure.
So then our